Today we'll describe the Schmidt process, which is an algorithm that takes as its input basis for a subspace. Well, the subspace could be all of Rn, but suppose we're given a subspace and a basis for it, and this basis is not necessarily orthogonal. And the whole point of Schmidt is to create a basis that is. And this turns out to be relatively straightforward. The first step is particularly easy, because any set with just one vector is necessarily orthogonal. So all we do is that we copy the given vector w1 over to v1, and that forms the first element of the orthogonal set. Then in the second step, this is where we're going to need to start to have to do some work. So now I have the vector from the, maybe draw it a little larger. So I have my vector from the previous step. So v1 is just w1. And now the trickiness is that the second vector, w2, it does not have to be orthogonal to v1. So we need to create a vector that is. And the way to do this is that we form the projection. So this vector is P2. And this is the projection of W2 onto V1. So what we do is we created the vector space capital V1. This is the span of the first basis vector. And then P2 is the projection of the next vector in the non-orthogonal basis, W2. I project that down onto V1. That gives me P2. And then the green vector here is my next basis vector. So V2 is W2 minus P2. Okay, I'm being a little sloppy about the boldface here, but I hope it's clear anyway. Okay, so now you see automatically by construction V2 sits in V1 perp, so V2 is necessarily orthogonal to V1. So now let's think about the third step. So where are we now? So we have two vectors. We've built two vectors, v1 and v2. These guys are orthogonal. Sorry for the flipping back and forth. I just want to try to use the same colors. So they span some space capital V2. So V2 is the span of V1 and V2. And now I am given the next vector. So the test now is that I'm given W3. And I want to build a vector V3 that's orthogonal to V1 and V2. So now you can probably guess what I'm going to do. I'm going to form the projection of W3. So this is my vector P3. Right? If we look here, you see that this is precisely the definition of the projection of W3 onto the space V2. And then the vector V3 is what remains. So it is this guy. So that's V3. And now by construction, V3 is necessarily orthogonal to V1 and V2, and that's the third one. Okay, so now you might wonder that we could run into trouble, run into a problem. What if V3 is 0? And question is, could that even happen? Well, what would happen if V3 is 0? So if V3 is 0, that's the same as saying that W3 is equal to P3, and P3, notice, is some linear combination. If we set that to be C1 and that to be C2, then this is C1 V1 plus C2 V2. And V1 and V2, they span the same space as W1 and W2. So there are some coefficients D1, so that I could write this as a linear combination of W1 and W2. I hope that step was clear, because V1 and V2 span the same space as W1 and W2. So now this equation here says that W3 is a linear combination of W1 and W2, which is to say that the set W1, W2, and W3 is linearly dependent, which contradicts the assumption that these guys form a basis. So this cannot happen. So when you use this process, you will always find a new non-zero vector, V3, that's orthogonal to the previous two ones. So this cannot fail. It's a very solid process. So if we generalize in the teeth step, then the formula looks like this, and you can envision exactly the same kind of picture as before, where you have the space spanned by the previous guys. So Vt minus 1 is the span of all the previous guys. And then we're given a new vector. So now in this step we're given, so this picture, it's exactly the same as before. We're given Wt, and then Pt is its projection. And Vt is this guy. So Vt is Wt minus Pt, which necessarily lies in the orthogonal complement to the previous vectors. So this is the Gram-Schmidt algorithm. So here I summarized it. So the input is any basis, the output is an orthogonal basis. And all the steps, except the first, look the same. Or if you wanted to, you could make the first step look the same if you set P0 to be 0, and then V1 would be W1 minus P0, which actually is exactly what happens if you take this sum and you plug in T equal to 1, because then you get the sum from 1 to 0, which doesn't exist. Or it has no terms, it's an empty sum. All right, but let's not try to be cute. So we'll formulate the process like this. Let's just review some properties. So these properties follow immediately from what we already, from our discussion. So first of all, so at the teeth step, you form Vt as a linear combination. So now we're comparing this expression to this. So Pt belongs to Vt minus 1. So in particular, you can write it as a linear combination of the Wj's, because Vt minus 1 is the span of the Wj's from 1 to t minus 1. Like so. So this is the first property. So so every one of the new basis vectors are formed as a linear combination of the previous ones. Then The next bullet point just states this fact we've already exploited several times. So at any intermediate step of the Gram-Schmidt process, the vectors, the orthogonal vectors that you've built, the VIs, they span exactly the same space as the corresponding vectors in the non-orthogonal basis. Then the next bullet point, it simply tells you what, gives you a meaning to what is this guy PT in the process. What's the orthogonal projection of WT onto this space, which we refer to as capital VT minus 1. So this is the span of the first T minus 1 basis vectors. And it doesn't matter whether you refer to the original basis or the new orthogonal basis, because they span the same spaces. And then VT, of course, by construction, is orthogonal to this span. And finally, the statement that the norm of VT, it's the distance between the next vector WT and the last linear space that you built. All right, so now let's just do a slight tweak to the algorithm. So say we want an orthonormal basis. So I want Vj to be 1 for all j, to have norm 1 for all j. So this can be done with a very, very minor modification to the algorithm. So all I do is that in the first step, I normalize the first vector. And then in the second step, I form the projection again, and now I see actually I goofed up a little because now V1 has length 1, so I don't need that step. So now the expression for P2 is like that, and then you just form the projection onto the orthogonal complement and you normalize. And you proceed, and again, these guys are not needed in this case because we have normalized. And you see that the process is basically the same. You don't need to divide by the length of the vectors in forming the projections, but you do normalize in the definitions of the VJs. So it's all very straightforward. Remember, you don't need these guys because they all equal to 1 in this formalism. And the main point here is that the process is basically the same. You just rescale the basis vectors that you compute. There is no fundamental difference whether you build an orthogonal basis or an orthonormal basis. So as a final example, let's do a numerical example. So we're given 3 vectors, W1, W2, and W3, and we want to build an orthogonal basis of vectors Vj. So remember, in the first step, we just take the first vector, and that forms the first guy in our orthogonal basis. So I'll show you the algorithm without the normalizing, just to save you a little bit of arithmetic. Then in the second step, I project, so P2, remember. This is the projection of W2 onto the span of V1. And the numerator here is W2.V1. Oh, did these backwards. So we have the formula. Just plugging in numbers, you get the thing over here. And if you work it all out, you get the following expression. So P2 is 1/3 times the vector 1, 2, 2. Then to build V2, we just take W2, we subtract the projection P2, and we get this expression here. So that's the second basis vector. So now you could check. So if you take v1 dot v2 just to make sure that these are linearly independent, well, this is 1/3 minus 4 minus 4 plus 8, and yes, this is 0. So it seems to have worked. So v2 is orthogonal to v1. The next step, I project w3 onto the span of v1 and v2. I get the following result. So here is the first term, there's the second term. Just work things out. And yeah, I'm saving you some numerical details, but if you work out all the arithmetic, you finally arrive at the vector v3 down here. And this is the final guy. Okay, so I'm not sure how helpful it is to just look at arithmetic calculations like this in a lecture. The way to learn this is really to work your own numerical examples, to make sure you do several runs on this, because this is an important technique. You are very likely to be able to need to use this in the future. So I recommend that you do lots of exercises. It sort of looks like there are lots of steps the first time you look at this, but it's really not all that daunting. Once you run a few examples and you get the basic ideas, I think you'll do just fine. You will, of course, make lots of arithmetic errors, so it's very easy to make minor errors, and just be careful, do the best that you can, and yeah, remember the exam is a take-home exam at least. So if there were to be an exam question involving Gram-Schmidt, you would have plenty of time to check your work. All right, that concludes this lecture.